Hey, this is a short video about sine and cosine waves, and I'm going to show you how to deal with the graphs of sine of x and cosine of x. So I already went over with you before. Let's focus. How about how sine is equal to opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. We've been over this, like blah blah blah, the mirror trick, and it's done all this before. But I didn't tell you why sine and cosine go together. Like, why do sine and cosine relate to each other? Why is it this thing and this thing? Like, how are these related? And I'm going to tell you in a second. No, I'm going to tell you right now. Sine and cosine make similar types of waves. If like tangent and cotangent make similar types of waves. Secant and cosecant make similar types of waves. We're just going to focus on sine and cosine right now, but if you enter like sine and cosine into a calculator, you'll see that they have similar waves. Just as if you do tangent and cotangent, you'll see that those two functions have similar types of wave, and the same goes for secant and cosecant. Those will have similar types of waves. So this is sine and cosine. I drew sine of x in pen and cosine of x in pencil. And the way that it works is like so. You got a circle, got an angle, and sine is this, and then this is done in radians, by the way, just so you know. And there are 4 points. There are like 4 crucial points in each function. So for sine of x, I'm going to do sine of x right now. If you got to remember this from the unit circle too. Remember the unit circle. We're doing the unit circle right now. So sine of x goes all the way up to 90 degrees, or pi over 2 radians. Also sine of 0 degrees or 0 radians is 0. Just put 0 for sine. And then it goes all the way up to pi over 2, and pi over 2 is 90 degrees, and sine of 90 is 1. I'm sorry, this is all crooked. And then you go, and the sine goes further. It goes over here, and it goes back to 0. What's sine of 180 degrees? Or pi radians? It's 0. You go back around, and then you got that, and you got at the bottom. Now sine is sine of 270 degrees is -1. You go around, back again to 0. So Aaron is like Aaron, how do you know all of these things? Like, how do you know that all of this is true? And I'll show you in a moment. But I want you to just take it for given that like 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians. I want to just like it be taken for given that like this is 0, this is pi over 2, this is pi, this is 3 pi over 2. This is all done in radians, which I explained a million times. So if you start at 0, okay, pi starts at 0, and then it goes to pi over 2 radians, and it goes to 1, and okay, it's at 1. And then you go to pi radians, and then it goes back down to 0. And then it goes to 3 pi over 2, and then it goes down to -1. And it goes to 0, and then it goes up to 2 pi. So, wow, like, boom, that's pretty great. It's pretty cool. It, like, follows the whole circle. It's like taking the circle, and let me zoom out. It's like taking the circle and then like doing this to it, like doing this. Oh, wait, no, that was shitty. Doing this, like that. Okay, yeah, sort of. And then for sine or cosine, whoops. For cosine, you got some different measurements. You have Sine of 0 radians is 1. Sine of pi over 2 radians is 0. Sine of pi radians is negative 1. Negative 1, I'll put it on this side. And then sine of 3 pi over 2 radians, or 270 degrees, is 0 again. And then that goes back to 1. I know you're thinking, like, how do I know this? But I'll show you. There's a shortcut. So it starts at 1, goes to 0 at pi over 2, or 90 degrees. Negative 1 goes down to negative 1. And then at 0 goes back to 0. And then when it gets to 2 pi, it's a full circle, so it goes back to 1. Just like how pi went back to 0. So it's like doing the same thing except a little bit differently for cosine. And like, how do I remember that 0 radians is 1 and pi over 2 radians is 0? And the thing is, in the unit circle, you got to remember like what's up with the unit circle and why it's important. I don't have anything here right now, but like, the thing is about the unit circle is that sine of x and cosine of x are equal to the coordinate points on the circle. So if you just assume that like the radius of this circle is 1, 1, 1, 1, then you have then sine of x is always equal to y. So here on this point it's 0. You go a little bit around and then it's 1, positive 1. Go a little bit around and then sine is equal to 0 again. Go around, it's negative 1. It's 0. Notice that sine corresponds to what's on the y-axis. So the y-axis is really the sine axis. Boom, there you go. And then you got to look at cosine. 1, because x is 1. It's 1 unit to the right, so it's positive 1. And then the x is 0 when it goes here because it's parallel the origin or whatever, because it's like right by the origin. And then you go around, and then the x is negative 1 because it's 1 unit to the left. And then you go down, and it's back at 0, and then it goes back to 1. So this is the cosine axis. So it's sine axis, cosine axis. And like, don't use sine axis and cosine axis in real life because no one's going to understand what you're talking about. But on the unit circle, the value of sine for any given value on the unit circle is represented by the y value. And cosine, it's represented by the x value. It's pretty great. It's really great to know. And that is sort of the derivation of sine and cosine. And if you want, for hypothetical purposes, like you can pretend to like draw an imaginary triangle on the unit circle. Like here is an imaginary right triangle that I just drew on a unit circle. Like this. And then here's the angle that you want to do it of. And so we can do like sine over 6 and sine over whatever. And to do opposite over adjacent and adjacent over hypotenuse. And that's how the unit circle kind of works. Because if you could sort of take any radius at one point and then make it the hypotenuse of a triangle and then turn it into like a right triangle here. And then like you can make it into its own angle and then figure it out. And so these are the hypotheticals for those 4 corners where if you drew a right triangle, it kind of would just be a straight line because it's just straight up or straight down. And that's important to know. It's important to realize about sine and cosine. Now I'm going to go over some derivation, not derivation, like what happens if you want to change the amplitude of the sine wave or like the period of the sine wave. Okay, here we go. So if you want to change the amplitude, 2 sine of x would be just like sine of x up here, except instead of going to 1, it would go to 2. So that's how you would change the amplitude. It's really simple. It's just like, it's like x, and then it's like 2x as a function, like y equals x, y equals 2x. You just put a times 2 multiplying the thing in front of it, and then you just make it twice as big. So amplitude changer, and it's like right there. Yeah, that's the amplitude changer, because you're just multiplying the whole thing by a thing. Now, if you want to change the period, that's a little more complicated. Sine of 2x. This would be the period changer. The period changer. So the period is like the length of the wave. It's like the other thing. And you would do that by, instead of doing it on the outside of the function, you would do it on the inside of the function. Because it's two different things. It's two very different things. One is changing the amplitude, and one is changing the period. So if you were to make the period of sine of 2x, it would still start at 0, but it would hit 1 at half of the whatever, like half of the time. Because if you're doing sine of 2x, you're making every point on the regular sine function hit its point twice as fast. So while you're doing that, while you're making it hit its point twice as fast, you're making the period half as long. So it's like inverted. So if you're doing sine of a of x, the period is equal to 1 over a. Because you're making everything happen that many times sooner, and you're therefore making the wave that many times shorter. So instead of like having a sine wave like this, because you're making every point hit it sooner, it would be like this. And you'd be making the period shorter because everything happens faster. Yeah. That's like changing the period versus changing the amplitude. And don't get this mixed up for period equals 1 over frequency, because that's something completely different. I'm saying that if you're doing sine times something of x inside the parentheses, the period is equal to 1 over that thing you're multiplying it by. This is just saying basically, like, if you're multiplying it higher, you're making the period shorter. If you're multiplying it lower, you're making the period go longer, because you're making it slower. Oh, actually, come to think of it, like, yeah, it is. It is like frequency. So this is like the frequency. If it's higher, the period's shorter. If it's lower, the period's longer. If you're in physics, this is really helpful. If you're not, just ignore everything I'm saying. Then there's, like, obviously sine of x plus 3. If it's on the outside, then it's fine. But if it's sine of x plus 3, then it's just like y equals mx plus b. You're just like, you just take the wave and then you like move it 1, 2, 3 units up. That's it. That's all you have to do. But if it's sine of x plus 3, it's like doing it for a quadratic function, like x minus 2 squared. And the way that works is that when you're adding, you're making things happen later, and when you're subtracting, you're making things happen sooner. No, that was wrong. When you're subtracting, you're making things happen later, and when you're adding, you're making things happen sooner. So actually, when you're adding, you would think you would be moving something to the right, but you'd actually be moving it left if you add, even though that's where the x's go negative, because you're making everything happen sooner. So everything would hit their points sooner. And if you were to do x at sine of x minus 3, then you would do it 3 units that way because you're making everything happen later. So you make it hit 1, 2, 3 points later in a positive direction, counterintuitively. So that's how you change everything. It's the same rules that you would think would apply to like a lot of other functions, like the quadratic function, and the linear functions, and like all these different functions, moving units to the right and to the left. Anyway, that's sine and cosine. Yeah, sine and cosine. Oh, also, if you are in calc and watching this for no reason, if you'll notice, here's sine going up, going up, going up, and then there's a critical point here, right when cosine is equal to 0, and it goes down, 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 and this is like the point of whatever, like maximum acceleration, and this is right when cosine equals 0. My point is that the derivative of sine of x equals cosine of x. And the derivative of cosine of x is actually equal to negative sine of x, counterintuitively. Because you'll notice that the cosine, if you try to do that with the cosine wave when it comes to the critical point, the sine wave doesn't correspond. But it does if you flip it. I don't know where the derivation for that is, like the actual proof. But if you look at the wave, you can tell that, cosine of x is the derivative of sine of x. If you weren't in calc, I'm sorry. That was a waste. That was kind of a waste of your time. Because there's no point in you knowing that. Yeah, that's it. That's all about cosine of x, of sine of x, about like the translations and stuff, and how they work. Have a great Sunday. Haha. Bye.